Welcome back to EGME-333 Fluid Mechanics. In this video, we're going to discuss incompressible flow in a duct. Before we begin, let's observe what happens to flow that travels through a duct. So what we see is that as flow travels from left to right in the duct, the cross-sectional area decreases. Consequently, each fluid element highlighted here or illustrated here as these initial squares tend to accelerate as the cross-sectional area decreases. So the question then becomes, why does the flow accelerate with a reduction in cross-sectional area? The answer to this question comes from the conservation of mass, which, recall, is defined as the net increase of mass inside a control volume is equal to the net mass flow entering the control volume across the control surface. Mathematically, the conservation of mass can be expressed with the following vector integral equation, where the left-hand term represents the net mass increase inside the control volume, and the right-hand term represents the net mass flow into the control volume across the control surface. However, to explain our situation, we have to make the following assumptions. If we assume that the flow is steady, incompressible, and that the control volume only has one-dimensional inlets and outlets, we can simplify the conservation of mass as simply m dot in must equal m dot out. Essentially, that the mass flow going into the control volume must equal the mass flow coming out of the control volume. Recall that the mass flow m dot is given to us by the density times the velocity times the cross-sectional area. So let's apply the conservation of mass to the incompressible flow inside a duct. Given that we have 2 points of interest, the inlet of the control volume, which corresponds to point 1, and the outlet of the control volume, which corresponds to point 2, we can say that the conservation of mass is equal to m dot 1 is equal to m dot 2, where again, the mass flow rate m dot is equal to the product of the density times the velocity times the cross-sectional area. Note that at point 1, we have a velocity v sub 1. At point 2, there's a corresponding velocity v sub 2. Similarly, at point 1, we have a cross-sectional area of a sub 1, and we have at point 2 the cross-sectional area given to us by a sub 2. So we can rewrite the expression for conservation of mass as simply rho 1 times v1 times a1 is equal to rho 2 times v2 times a2. I've stated that I am assuming that the flow is incompressible. And mathematically, that means that the density at point 1, rho sub 1, must equal the density at point 2, rho sub 2, where the density is essentially uniform throughout the flow, which often we simply write as the density rho. However, for this problem, we can identify that both the left-hand side and the right-hand side of the conservation of mass equation has a density, rho sub 1 and rho sub 2 respectively. By assuming that the flow is incompressible and that these two quantities are equal to each other, we can simply cancel them out from the entire expression, which simplifies the conservation of mass to v sub 1 times a sub 1 equals v sub 2 times a sub 2. So let's see what happens to the flow as it travels through both a converging duct and a diverging duct, where, again, in both cases, the quantity that's going to be conserved due to the conservation of mass will be the volumetric flow rate, capital Q, which is simply the product of the velocity times the cross-sectional area. Also, we want to consider what's happening with the pressure of the flow. So we'll pull in the Bernoulli equation, which will apply at both the inlet point 1 and the outlet point 2. But first, we'll focus in on the converging duct, where at the inlet we'll have velocity v sub 1 and we'll have the local static pressure p sub 2. Now, because the duct is converging, that means that the cross-sectional area is decreasing with axial position. Therefore, the area at the outlet, a sub 2, is less than the area at the inlet, a sub 1. Now, because of the conservation of mass, in order to conserve the volumetric flow rate capital Q through the duct, then because the cross-sectional area decreases, this leads to an increase in the local velocity. Therefore, V sub 2 is greater than V sub 1. The velocity at the outlet point 2 is greater than the velocity at the inlet point 1. So we can argue that if the area decreases along the flow, such as in a convergent duct, the velocity increases. To consider what happens to the pressure, we can utilize the Bernoulli equation. Now, because the flow increases in a converging duct, this leads to a decrease in the local static pressure, where as the flow accelerates, we have an increase in dynamic pressure, and consequently, for a horizontal flow, this leads to a decrease in the local pressure. So P sub 2 is less than P sub 1. Now let's consider the case of a diverging duct, where in a diverging duct, the velocity at the outlet, a sub 2, is greater than the velocity at the inlet, a sub 1. Now at the inlet, we have our corresponding inlet velocity v sub 1 and the local static pressure at the inlet p sub 1. Now, because the cross-sectional area is increasing, because of the conservation of mass, this is going to lead to a decrease in the local velocity, where v2 is going to be less than v sub 1. So in a diverging duct, if the area increases, then the velocity decreases. When we consider the question of pressure, because of the decrease in the velocity, this leads to an increase in the static pressure, where P sub 2 is going to be greater than P sub 1 due to the Bernoulli equation.